Explore motor control simulation, phase currents, space vector modulation, and torque speed response.
See how the results are, how IA, IB, come out in the simulation. This is your alpha beta, which is also sinusoidal because they are on the stationary reference frame. So they are time varying. And then you have got your D and Q. You can see what happens during perturbation, and then you can see that at steady state it's a fixed value, and then during perturbation you have these values here. Only ID 0 under steady state. So this is this is your back EMF signal of phase A. Phase A current lines up very well, and that's something I'm always watching when I'm looking at a motor control, is how well the phase current matches with the back EMF. All right, and you can look at here, this is your error amplifier output for A, and alpha and beta, error amplifier output for beta, which is the PI loop output. And this is your error amplifier, and this is your PI loop output for A, B, and C. And this is your torque speed response, essentially what happens to your torque as you increase your speed. So you have initially high torque, and then it begins to slow down. So this basically becomes your base here. So that is your quick PSpice simulation, which you can simulate, or you can do it in some other mechanisms as well. Now let's spend a few minutes on space vector modulation. Before I go to space vector modulation, are there any questions I can answer? Okay, no questions. Let's move forward.
Yes, sir. I have.
Yes, go ahead, Simba. Yeah.
Okay, so in one of the slides, you talked about three-phase sine inverter generating duty cycle, where we have this amplitude modulation ratio. So when we are using, if suppose sinusoidal SVPWM, in that case, this MA will be same for all the phases, or it will be different?
So you're using space vector modulation in sinusoidal, is that what you said?
SPWM, if we use in FOC loop, so from the current loop we get voltage reference, right? That voltage would go to three phases.